In this video, we are going to talk about binary trees, which is again one of those very useful data structures. A binary tree is a reference-based data structure. So in a sense, it's going to be similar to linked lists, which probably you have studied before this video. But the difference between the linked list and the binary trees is that a binary tree is going to have two references in every node instead of just one. You remember linked list, a typical linked list has a reference called next that refers to the node that goes after a particular one. So in a binary tree, those two references are called the left and the right child instead of calling it next. This is a typical diagram of a binary tree. And as you can see, we have these things which are the nodes, and they have letters in this case. But then you see that there are two references, okay? And this reference here, as you can see from the graph, is called the left child, and this one here is called the right child. So we said that a binary tree, and that's why it's called binary tree, because every node has up to two children, has a left and a right child. It is called a tree because if you turn this picture upside down, then this will be the root of the tree, which actually this node is called the root and is very important. And then the tree starts branching out. This is what is called a binary tree. It's an upside down tree, and every node has up to two children. That's what is called binary. There are other type of trees which are not binary trees, in which the nodes can have more than two children. So some terminology, as you can see here, is this node is very important. This node tells us where the whole tree is going to start, and this is called the root. So typically we're going to have an external reference that is going to let us know the address of that node, the address of the root of the tree. And that's the only information that we need to move around when we talk about binary trees. This is very similar to what we did with linked lists. If you remember, a linked list has an external reference called front, and that front tells us the address of the first node. So the equivalent thing on the binary tree will be to have an external reference called root, and that root tells us the address of the node that is located at the root. In addition to having a left and a right child, we talk about parents and siblings. So for example, we said that A, because A has a left child which is B and a right child which is C, then we said that the parent of the node B is A, the parent of the node F will be C, the parent of the node E will be B. So we talk about parents and children. We also talk about siblings. For example, D and E are siblings. Why? Because they have the same parent, which happens to be B. B and C are siblings because those two have the same parents, which happen to be A. There are two other important terms that we use in binary trees. Those are leaves and subtrees. So what is a leaf? Notice that these nodes at the bottom, D, E, F, and G, have no children. They have 0 children. So a node in a binary tree that has 0 children is known as a leaf. Again, we're using terminology borrowed from a real tree. What is at the end of the tree? We start probably with the root, then the trunk, then the branches, and after the branches we have leaves. So the nodes at the bottom of a binary tree are the ones without children, and those are called leaves. And then we have subtrees. You are going to see when you take a look at the code that we provide for you, building a binary tree and most of the operations on a binary tree are done recursively. So I can say that node A has two children, B and C, but node B has two children, which is D and E. So I could say that I can isolate with this circle here the nodes B, D, and E, and that is a subtree, it's a section of the tree. And again, it matches the definition. Every node is going to have 0, 1, or 2 children at most. And then we talk about left child and right child, we talk about leaves, and then we could consider this to be a root for this subtree. So in a big picture, in the binary tree, we talk about the left subtree. Those are all the nodes to the left of A, all the nodes, quote unquote, hanging from the left child. And we talk about the right subtree. The right subtree are all the nodes which are hanging, quote unquote, from the right child of A. But then I could say also, because this is a recursive definition, that G is the subtree of C, or that D is a subtree of B, so on and so forth. So spend some time taking a look at this picture and make sure that you understand what a root is, what a parent, the left, the right child, leaves, right subtree, and left subtree. Now, let's talk about the code and compare that a little bit to the code that we use when we implement the class myNode. As you remember, myNode was the class that we use to implement a linked list. So I have slightly modified the myNode, and now I call it myBtNode, BT for binary tree. And again, we're using the same idea of having a placeholder so I can store here objects of any kind that I want. And every node is going to have the object which contains the data and then two references. You remember the myNode class in the linked list has only one reference called next. Here we're going to have two references. One we call it left and one we call it right. Left for the left child, right for the right child. And both of them are recursive definitions because both of them are references to something that we call myBtNode. Consistent with this, then I need to modify my constructor. Then my constructor is going to have three parameters. So instead of data and next, like we did in the linked list, this is going to have data, left child, and right child. And then I'm going to use the mutators to assign the values to corresponding fields. So this is going to change the value for the data field, this is going to change the value for the left child, and this is going to change the value for the right child. And down below, I'm not showing you the entire code, but I'm showing you the signature of the method that we expect to see, right? We have three fields, data, left, and right. So we expect three accessors and three mutators. So here are the three accessors, the methods that allows us to change each of the fields. So one to change the data, one to change the left child, and one to change the right child, and each of them has the necessary parameters. And then we have three accessors, which are the get data that retrieve the object, store in the data field, get left, and get right are going to give you a reference to the left child of the node that you're inspecting, or a reference to the right child of the node that you are inspecting. So as you can see, the modifications are very basic. All right, now let's talk about some terms which are very important, all right? So we talk about levels on a binary tree, we talk about the height and the depth of a binary tree. So let's start with levels. First of all, this is a typical binary tree, okay? Again, every node has 0, 1, or 2 childs at most. So here you see that I have put the depth. So let's start with the bottom definition. What is the depth? Depth is the length of the path, okay? Numbers of links from the root to the node. So if I'm this node, okay, and I'm trying to establish the numbers of length, what is the length of the path between this node and the root node? Well, it's only one link. So I'm going to say that the depth is 1 between these two nodes. Now, if I'm talking about the root, so I'm talking about the length, the numbers of paths, and the numbers of links between the root and itself. Well, between the root and itself, there are no links. Therefore, the depth is 0. If I'm down here, okay, what is the depth? Again, I'm going to count 1 link, 2 links, and 3 links. So I'm going to say that the depth of all these nodes actually here is of depth 3. Okay. Now, the height is the longest path. So it's not just the length of any particular path in between two nodes, but it's the longest path between a root and a leaf. So how many leaves do I have? Well, I have 8 leaves. Okay. Each of these 8 nodes is considered a leaf. So what is the longest path? Well, the longest path will be something like this. So if I do that, how many links do I have? Do I have 3 links? So I'm going to say that the height is 3. If I pick this leaf, again, I could follow this path, and that's 1, 2, 3 links. The height is 3. This node here, okay, I'm following this path, 1, 2, 3 links. Okay, so the height of this tree is 3. Last, what is levels? Not being shown on the picture, but the best way to think about level is 2 ways. Numbers of parents of a nodes on a tree. Okay, so let's count the numbers of parent nodes. Well, obviously this is a parent node, So I have 1, this is another parent node, 2, this is a parent node, 3, and that's it. Okay? So I have 3 levels in this binary tree. These nodes here, they are not parents of any node because they don't have children. They are leaves. So they cannot be parents by definition. So I have 1, 2, 3 possible nodes that can be parents. So I said that level is 3. The other way to think about this is by drawing an imaginary horizontal line. Okay, so let me draw a horizontal line here. So that will be 1 level. And that level only crosses the root node. If I draw another horizontal line here, that line will cross these 2 nodes. If I draw a horizontal line here, it crosses these 4 nodes. And again, the only other possible horizontal line is one like this that will go across these 8 nodes. Okay, so how many horizontal lines do I have? I have 1, 2, 3, and 4 possible horizontal lines. And we said that the very first one is called level 0, same thing as depth 0. The second line will level 1, next one level 2, and next one level 3. So I can talk about the nodes at level 2 or the nodes at level 3, or I can simply say that this binary tree has 3 levels. So I can use the height to figure out how many levels I have, or I can use levels to figure out what the height of the tree is going to be. All right. Okay, now shapes, which is very important for the applications of the binary tree. Okay, there are many different shapes, and I'm going to concentrate on the 3 more important shapes in a binary tree. And those are full, complete, and balanced. And it's important that you understand these concepts because in future videos we're going to refer to a full tree, a complete tree, and a balanced tree. Okay, so here is a picture of a full binary tree. What does it mean that it's full? It means that every node is going to have either 2 children or none. So let's take a look. Pick any node. If you pick this node, it has 2 children. If you pick this node, it has 2 children. If you pick this node, it has 0. This node has 0. This node has 2. Any node that you will pick on the tree will have either 0 or 2. So what is missing? Nodes that have 1 child. Okay, it will be impossible. Another way to look at a full tree is we were talking about levels. Okay, horizontal lines across the binary tree. Remember that? So we can say also that a full tree is using all the possible nodes, locations at any given level. So if I draw a horizontal line here, I have a possibility of having 4 nodes. Well, I do have 4 nodes. In the next level, I have 8 nodes. At this level, I have 2. And notice, by the way, that there's a relationship here with powers of 2. This is 1 node, 2 to the 0. This is 2 nodes, 2 to the 1. These are 4 nodes, 2 to the 2. The next level is going to have 2 to the 3 nodes, which is 8. The next level will have 16. Okay? So a way to take a look at a full tree is to say, well, if I go to level 4, okay, that will mean 16 nodes. I need to go to level 4 and see if I have 16 nodes. If I have anything less than 16, then it's not full. Complete. Complete is almost a full tree, but it's only a full tree up to the next to the last level. So talking about levels again. So I don't have a picture, but for a while, for a couple of seconds, assume that these 4 nodes are not in the picture. Okay? If they're not in the picture, then this will be a complete tree. A complete tree because up to this level, it is a full tree. Full tree meaning that every level is being used. Okay? So again, if you eliminate these 4 nodes or any of these 4 nodes, then it's not a full tree, but it will be complete because up to this level, which is next to the last level, right, is complete. And finally, we have balance. And balance have to do with the height, which we studied earlier. So let me go again and refresh you what the height is the longest path from the root to the leaf, right? So a balance uses a definition of a height and the definition of right and left subtree. Remember, all these nodes are to left of the root, so this is the left subtree of my entire tree, and this one is the right subtree. Okay, so I need to measure then the height of both. So if I measure the height, as we saw in the picture before, the height is going to be 3. So the height of the left subtree is 3. The distance from the root to the leaf, okay, is 3 links. Height is 3. Now the right subtree obviously have to have the same height because visually we can see that they're at the same level. So again, if I start here, that's 1 link, 2 links, 3 links, so also the height is 3. So I conclude that because the height of the left and the height of the right are the same, that is a balanced tree. Now, let's assume that these 4 nodes are not here, okay? Let's assume that we delete these 4 nodes. So the height then of the left subtree is 2. Again, remember, these nodes are not here. So 1 link, 2 links, so the height of the left will be 2. The height of the right, okay, continues to be 3. So the difference between the two heights, this one is 3, this one is 2, will be 1. So we'll say that is also balanced. Now the extreme case will be what happens if there is no, let's say, left subtree. All these nodes are gone, okay? So the height of the left subtree is 0. The height of the right subtree is 3. So the difference between the two heights exceeds 1, and therefore is not a balanced tree. Once we study binary search trees in a different video, you're going to see that the idea behind full trees, complete trees, and balanced trees is extremely important. All right, what are the applications of binary trees? There are many, and here I'm just giving you a couple of them. Let me start at the bottom one. Well, probably the most important application of a binary tree is what we call binary search trees, which are binary trees that they're built using a very specific rule, and as the name says, are strictly used to search for values. There is a separate video in which we study binary search trees and we compare a binary search with other searches that you probably are familiar with, like linear sequential search and binary search. But that's a very important application of binary trees. Another application is expression trees. In other words, we use a binary tree to store and evaluate expressions that you use quite often when you write programs. So, for example, let me show you this picture and we'll come back to it to explore in detail. This is what is called an expression tree. Notice that the values of the nodes are either operators like addition, multiplication, division, so on and so forth, but there are also some nodes which are operands, the one that has the values A, B, D, E. This binary tree that you see here is actually storing this expression. And this expression is the addition of two values. The value that comes from the multiplication of D and E, and the value that comes from the subtraction of A minus the division of B by C. And notice that are parentheses. So why do we use binary trees to represent that expression? Well, there are actually 3 reasons. First, here we're using parentheses. So somewhere we have to store these parentheses in memory. So there is memory that is being used because of the parentheses. If I use a tree, notice that there are no parentheses. The nodes are either operands or operators. There are no parentheses. So I'm saving memory. The second thing is, every time that we use parentheses or any sort of grouping symbol like brackets, you need to make sure that they're balanced before you can evaluate. So you're going to spend some time, you're going to spend computer cycles trying to decide whether or not this is balanced with respect to the parentheses. Now, with the binary tree, we eliminate that problem because there is no parentheses to check. So that's the second advantage. And the third one is that we may need to know the evaluation rules for that particular language and that particular expression. And here, we're simply traverse the tree in a very specific way that is going to allow us to evaluate this expression. So a very common application of a binary tree are expression trees. And finally, we have another common application, very important, which is decision trees, which are used in many fields, not only in computer science. They're used in psychology, they're used nowadays in medicine. So we can use a binary tree to represent any sort of decision diagram or process. Why? Because we're using sort of like yes-no questions or true-false questions, all right? Let me give you an example. Let's say that here you ask the question, are you a male student or a female student? Well, that's a yes-no question. It's also a question that has only two possible answers. So one answer, let's assume female, we go to the left. If you are male, then you go to the right. So let's say now that you answered that you are female, and now here we said, are you sitting at the right of the room or on the left of the room? And again, that's a question that has two possible answers, left and right of the room. So here's the left of the room, right of the room. Now let's say that the person answered, I'm sitting at the right of the room. Then finally, we ask the question, are you sitting at the front of the room or the back of the room? Again, another question with two possible answers. So that's what is called a decision tree. Now, they're used nowadays in medicine. For example, are you male or female? Are you in pain? Yes or no? Do you have fever? So it's a decision tree that is built using questions that has two possible answers. One thing that we need to discuss is how to traverse a binary tree, because this could be kind of tricky. It's not a linear data structure as we are used with linked lists and arrays. It has a right child and a left child, and it has a right subtree and a left subtree. So there are many ways of traversing the trees. Basically, there are three ways of traversing the tree. I'm going to discuss two of them in this lecture. And then in a future video called Binary Search Trees, we'll discuss the third method to traverse the tree. So as explained earlier on in this video, one way to traverse the tree is called pre-order traversal, and the other one is called post-order traversal. And one basic applications of these two is how to come up with an expression using pre-order notation or the same expression using post-order notation, and I will show an example in a couple of minutes. Basically, pre-order traversal, as the word says, means that you are going to traverse the tree. We're going to visit all the nodes on the binary tree in pre-order, and that means that we first go to every node, then we visit one node after the other. But every time that we go to a node, after we do whatever we're doing, in this case we're going to, let's say, print the nodes, then we need to go to the left subtree of that node and then visit all the nodes there, and then we come back to the node and then we go to the right subtree and then we visit all the nodes of the right subtree, and then we go back to the node, and we apply this rule recursively. So we said that pre-order traversal basically is node left right. Do whatever you need to do with the node first, then process its left subtree, and then process its right subtree. So here we have the binary tree that we have discussed. And the way to traverse this using a couple of tricks that are very helpful. So one trick is to draw this curve that you see with dash hyphens, okay, going as close as you can through all the nodes that you have on the binary tree. And what we're going to be doing is drawing this curve counterclockwise in that motion. So we start with this little square box is, we go around the tree traversing the nodes, and then we end up right here where the arrow is. The second step is to place a marker or a dot in every node. There are three possible places to place that marker around the node. So as you can see here, the node that has the F, it has a little dot to the left of it. The second option is going to be to place it below between the left and the right child, or in between those two children. And the third option is to place the marker here on the right hand side. Because this is pre-order, part of the technique I'm showing to you is to put the markers on the left side of the node. So if you see, every node that I have in this picture has a little dot to the left. Now, to traverse the tree, I'm going to use then the curve and the dots. So I start where the black box is, and I'm going to move, as I said, counterclockwise. So I start on the square, follow the curve, and every time that the curve intersects the marker, then let's say I'm going to print that node. So here, the first intersection of the curve and the marker is for the node f. So if I were to, let's say, print the nodes, the first value that will print is f. And then I continue traversing, following the curve, and I see again that there is an intersection here, so the next node to be printed is b, and then the next node will be a, and the next node will be d, and then followed by c, and then followed by e. Okay, now I'm saying printing. It could be that you want to modify the values, or you want to compare them looking for a particular value or particular characteristic. So visiting a node means doing whatever you need to do in the particular task, whether it's printing or changing the values. So if we keep going through the node, notice that when we go to the very root, okay, the root has already been printed because there is no intersection here. The intersection was at the very beginning. And then we follow through, and then we intersect the two markers with the curve in G, and then we process G, we process I, and then we process H, and that will be the last node to process because there is no other intersection. So in a pre-ordered traversal, which again is not left or right, the first node to be printed is always the root because the technique says process the node first, and obviously the root is going to be the first node. Now, if you start at any particular node in any subtree, you apply the rule recursively. In other words, if you are starting here in D, well, again, if you follow the curve, says, all right, we're going to process first D, then we're going to go to the left subtree and process all the nodes. Well, there is only one node, so after printing D, we print C. We go back to the node that we came from. Now we do the right subtree. Okay, there is only one node, so we print E. So processing this subtree will be in that order, D followed by C followed by E. And once we're done with this, notice that we're done with the right subtree of B. So at this point, we're done with all this, right? We're done with the last subtree of the root of the tree. Now we got to process the right subtree. So what do? First, go to this node, and when you look at the code, we first try to go to the left, but there is nowhere to go. So then we go to the right, and that says, oh, I need to do I. And on I, that means first go to the left, and then we go to the right, and there's nothing to do, and then we come back, and then we come back to the tree. So this rule, node, left, right, is being applied recursively at any node that you start. But using this curve and using the markers helps us to understand at the beginning how that works. Now let's talk about the post-order traversal. So the post-order traversal processes the node last. So we first go to the left subtree, then we go to the right, and then the last thing that we do is the node. So in other words, that's in a sense the reverse order of what we did with the pre-order traversal. So again, we're going to use the same trick. We're going to draw a curve that starts at the root and move counterclockwise and ends at the root. And then we're going to put markers. But because this is a post-order traversal, the markers now are at the right of every node instead of being on the left of every node. And then just go through the curve and find the intersection. So notice here that although we start at the root, there is no intersection of the marker with the curve, so we don't do anything with F. So we don't print F in a sense. Same thing happens with B. We don't print B. And the same thing happens at the beginning with A. And why is that? Well, because recursively we're saying every time that you go to a node, go to its left subtree. So every time I go to a node, I go to the left, and then a new node, I go to the left, and a new node, and then go to the left, but there is no left. And after we go to every left subtree of every node, again, recursively, we go back to the node that we started from, and then we say, okay, let me go to the right subtree and do the same thing. And after we have traversed or processed all the nodes on the left and all the nodes on the right subtree of a particular node, then the last thing we do is to print or modify or compare that node. And that's what is called post-order traversal, because whatever operation we do with the node is done after we recursively traverse all the left subtree and all the right subtree of that node. So continuing with this diagram, right, what happens here? The first intersection is here. That means I'm going to print A. Now let's reason why. Again, we started at the root F, we go to the left, we move to B, we go to its left, we go to A, we go to its left. There is nothing, there is no left subtree. We go back to where we came from, that's A. we go to the right subtree of 8, which doesn't exist. So at this point, we have processed the left and the right subtree. So what do we do now? We process the node, post-order traversal. In this case, print the node. Let's continue. So we follow the curve. We're still not accessing B. We do not access D. And here we access C. And again, why is that? Well, let's see where we came from. So starting with B, we went to the left and we processed the entire left subtree, right? We printed A. So now we had to do the right subtree. So the right subtree says, okay, starting B, go to the right, that is D. Oh, new node, apply rules recursively. First, I have to go to the left, and there is a left. And when I get to that node, recursively again, go to the left. There is no left subtree. Then go to the right. There is no right subtree. Last thing we do, process, in this case, print that node. So we print C. Again, came from D. We move to the left because that's what the rule says. Well, now we're done processing the left subtree. We printed C. What's next? We need to go to the right subtree of D. So notice that we are here. And again, we're going to go to the left first. We're going to go to the right then second. There is nothing to be done because there are no children in here. Then we process the node. And rightly so, we follow the curve, says that after printing C, we print E, and then D, B, and at this point, if you're coming from F, you have done, or we have done, all the left, so now we need to do all the rights. In other words, in a post-order traversal, we're going to process, we're going to visit all the nodes that they are on the left subtree first, then all the nodes that are on the right subtree first, and the very last thing that we do in a post-order traversal is to deal with the node at the very root of the tree. In that way, the two traversals are the opposite from each other. Here, the first node in pre-order traversal, the first node that we process or revisit is the root, because pre-order means first the node, then the subtrees. On the other hand, in post-order traversal, what we do is first the subtrees and last the nodes. So we cannot process the root of the binary tree first. We have to process the entire left subtree, the entire right subtree, and the last thing that we do is to process the node. In a future video, we'll do in-order traversal, but you can guess what in-order will be. Okay, it means that we're going to be doing first the left subtree, then the node, and then the right subtree. But that will be on a future video. One application of pre-order and post-order traversals, as I said, is what is called expression trees, which is a very common, very useful application of binary trees. So notice that typically we will have this expression, okay? In any programming language, and specifically in Java, we use operators to perform in operands. So A, B, C, D, and E are operands. So we're doing subtraction, multiplication, and then we use parentheses to specify what operation we're trying to perform first. This clearly indicates that we're dividing B by C, and then that value is being subtracted from A. And then the other thing that we do is to multiply D times E, and then we'll take the result of this evaluation and we add it to the result of this multiplication, and that's the result. So if I were to put that into a binary tree, this is the way it works. So notice that the last thing that we did was to add. So add becomes the root of the entire tree. And then in this very simple expression, there are two things that we're doing. Here we are subtracting two values. So again, the operator becomes the root of a subtree. Here we're multiplying two values. Here the root of the subtree is the operator. And then here is very simple. We're multiplying D times E. Here we're subtracting two things. What? A. And then we are subtracting again the division of two values. So the operator again is a root, and the children's are the operands. So there are two ways to rewrite this expression, using what is called prefix notation or postfix notations. If I were to use prefix notation, this is exactly what you see. And prefix means, remember, node first, then left subtree, then right subtree. But in this case, the nodes which are not leaves are all operators. And prefix notation means the operators are at the beginning. Postfix notation, on the other hand, means exactly the opposite. The operators tend to be at the end. So look at this expression tree where the addition is. And remember, the addition is the last thing that we're going to do to evaluate the expression. In a prefix notation, the first thing that shows up is that operator, the addition. In a postfix notation is the last one. And again, if you remember the discussion from 2 minutes ago, that makes sense. In a prefix traversal, the root is the node that we process first. That's the addition. And in postfix traversal, the root of the entire tree is the one that we process last. So let's just take a look at this, for example. So if we do pre-order traversal, and again, you can draw the curve and put the markers. So the curve will be coming down here, right, like I'm doing with the mouse, and then the markers will be to the left. And that means, oh, we're going to do multiplication first, right? And then the curve will come here and says, oh, I'm meeting the node that has D, so it's a D, and then it goes around and it meets the node which is an E. So it will be multiplication or times DE. If I do a post-order traversal, remember, again, is the same curve counterclockwise, but now the markers will be to the right of every node. So when the curve comes here, it's going to say, okay, I don't see the multiplication, I don't see D, oh, I see D, and then the curve come here, I don't see multiplication, I don't see E yet, and when I get to the side, I see, oh, now I'm processing D, and then the last thing will be, oh, multiplication. So it's D, E, times, and that's exactly what you see here, DE times. Again, the operator in postfix is at the end after the operands. The prefix notation is the other way around. The operator is at the front. Okay, I encourage you to watch the video on binary search trees and look up the traversal in order of binary search trees, because when you have binary search trees, it makes more sense to traverse the tree in order. Plain binary trees like expression trees, you can do a pre-order or a post-order traversal.